Picture this, a single day when the course of life on Earth changed forever. Not through collision with an asteroid, not through war or catastrophe as we might imagine it, but through a cascade of environmental changes so profound that they reshaped the entire planet. 252 million years ago, Earth experienced what scientists call the Permian-Triassic extinction event, the most significant biological transition in our planet's documented history. Today, we're going to explore the science behind this pivotal moment, understand what triggered it, and discover why studying this ancient event helps us better understand the world we live in now. This isn't a story about destruction, it's a story about transformation, resilience, and the incredible mechanisms that govern life on our planet. What scientists have discovered about this period reveals something extraordinary about Earth's systems and the delicate balance that sustains life as we know it. Before we dive into this remarkable period of Earth's history, it's worth understanding how scientists actually know what happened 252 million years ago. The story of the Permian-Triassic transition is written in rocks, preserved in chemical signatures, and decoded through decades of careful scientific detective work that spans the globe. Geologists first noticed something unusual in rock formations from this period in the early 20th century. In locations as diverse as China, Italy, Iran, and the western United States, they found the same puzzling pattern. Rocks rich in marine fossils would suddenly give way to layers almost completely barren of life, followed by rocks containing entirely different types of organisms. This pattern was so consistent and so dramatic that it marked one of the most obvious boundaries in the geological record. What scientists discovered next was even more intriguing. Chemical analysis of these boundary rocks revealed dramatic shifts in carbon isotope ratios, indicating massive changes in the global carbon cycle. Ocean sediments from this period show evidence of widespread anoxia, oxygen depletion, while terrestrial rocks reveal signs of dramatic climate shifts and vegetation changes. Perhaps most remarkably, this same geological signature appears on every continent, providing clear evidence that whatever happened during this period affected the entire planet simultaneously. This global nature of the evidence was one of the first clues that scientists were looking at something far more significant than a regional environmental change. To understand the magnitude of what happened 252 million years ago, we need to step back in time and see the world as it was during the late Permian period. Earth looked fundamentally different then. The continents were joined together in a massive supercontinent called Pangaea, stretching from pole to pole like a giant puzzle piece assembled from familiar shapes we'd recognize today as Africa, South America, North America, and Asia. The climate was warmer than our modern world, with no ice caps covering the poles. Instead of the scattered land masses and vast oceans we know today, there was one enormous continent surrounded by a single, planet-spanning ocean called Pangaea. This configuration created unique weather patterns and ocean currents that had been stable for millions of years. The interior of Pangaea was dominated by vast desert systems, some larger than any desert on modern Earth. These arid regions were bordered by more humid coastal zones where most life flourished. The single global ocean created different circulation patterns than we see in today's multiple ocean basins, with massive currents that transported heat and nutrients across planetary distances. Life had been flourishing in this Permian world for over 40 million years. The oceans teemed with diversity that would seem alien to us today. Massive coral reefs, built not by the corals we know now but by ancient organisms called rugose and tabulate corals, created underwater cities that supported complex ecosystems. These reefs were architectural marvels in their own right, some stretching for hundreds of kilometers and creating shallow lagoons that served as nurseries for countless marine species. Brachiopods, which look somewhat like modern clams but are actually quite different, filtered nutrients from the water in enormous numbers. Some species grew to sizes that dwarf any modern filter feeders, indicating how nutrient-rich the Permian oceans were. Trilobites, those iconic armored creatures that had survived for nearly 300 million years, continued their ancient success story in the deep ocean, having adapted to virtually every marine environment on the planet. The ocean depths were home to creatures that seem almost fantastical today. Giant sea scorpions patrolled the seafloor, while primitive sharks with unusual fin arrangements cruised the open waters. Crinoids, sea lilies that are actually animals, not plants, created underwater forests that swayed with the currents, providing habitat for countless smaller organisms. On land, the story was equally remarkable. Forests of seed ferns and early conifers covered much of Pangaea's humid regions. These weren't the flowering plants that dominate today's landscapes, those wouldn't evolve for another 100 million years, but they created rich ecosystems nonetheless. Some of these trees grew to enormous sizes, creating forest canopies that supported complex communities of insects, early reptiles, and amphibians. The seed ferns were particularly important because they had developed some of the first truly drought-resistant reproductive strategies, allowing them to colonize areas that had previously been too dry for large plants. This expansion of forest ecosystems had been gradually changing Earth's atmosphere for millions of years, creating more stable oxygen levels and more predictable seasonal patterns. Early reptiles were diversifying into forms that would eventually lead to dinosaurs, though that evolutionary explosion was still in the future. Some had developed the ability to regulate their body temperature more effectively than their amphibian ancestors, giving them advantages in the variable climates of Pangaea's interior. Others were experimenting with different feeding strategies, from specialized plant-eating adaptations to more sophisticated predatory behaviors. Perhaps most significantly, life was becoming increasingly complex and specialized. Ecosystems had developed intricate relationships between species that had taken millions of years to establish. Predator and prey relationships had reached sophisticated levels of adaptation and counter-adaptation. Plants and their animal pollinators had co-evolved complex partnerships, while soil ecosystems had developed multi-layered communities of decomposers, root symbionts, and nutrient recyclers. What scientists find most remarkable about the pre-extinction world is how robust these systems appeared to be. This wasn't a fragile biosphere teetering on the edge of collapse. These were mature, established ecosystems that had weathered previous environmental changes and continued to thrive. The diversity of life forms suggests that Earth's biological systems had reached a new level of sophistication and stability. Evolutionary innovations were occurring at a steady pace, but within the context of stable environmental conditions. Species had time to develop highly specialized adaptations because they could count on their environments remaining relatively consistent. This specialization, while beneficial in stable conditions, would prove to be a vulnerability when rapid changes began. Yet within this apparent stability lay the conditions that would soon trigger the most profound biological transition in Earth's history. The very success of Permian ecosystems may have made them more vulnerable to disruption, as highly specialized organisms often have fewer options when their specific environmental requirements change rapidly. The transformation began, as far as scientists can determine, in what is now Siberia. Massive volcanic systems known as the Siberian traps began releasing enormous quantities of lava, gas, and ash into the atmosphere. But this wasn't a sudden, explosive eruption like Mount Vesuvius or Krakatoa. Instead, it was a prolonged period of volcanic activity that continued for hundreds of thousands of years. To understand the scale, imagine volcanic eruptions covering an area larger than the European Union, continuing almost continuously for a period longer than all of recorded human history. The Siberian traps released enough material to cover the entire continental United States under a layer of lava several feet thick. Some individual eruption events released more volcanic material than all of recorded human history's volcanic activity combined. The geological evidence for these eruptions is staggering. In some areas of Siberia, volcanic rocks from this period are stacked more than 3 kilometers thick. Chemical analysis of these rocks reveals that they were formed from some of the most intense volcanic activity in Earth's known history, with magma temperatures and eruption rates that exceed anything in the modern world. What made this volcanic activity particularly significant wasn't just the lava itself, but what came with it. The eruptions released massive quantities of carbon dioxide, sulfur compounds, hydrogen sulfide, methane, and other gases into the atmosphere. Modern estimates suggest that these eruptions released more greenhouse gases than all current human industrial activity produces in several centuries, and they did so over a period of hundreds of thousands of years. The sulfur compounds were particularly important because they created acid rain on a planetary scale. This acidification affected both terrestrial and marine environments, dissolving calcium carbonate structures and altering soil chemistry across vast regions. The hydrogen sulfide was toxic to most forms of life and may have created poisonous atmospheric conditions in some regions. These gases began altering Earth's climate systems in ways that created cascading effects throughout the planet's interconnected systems. The first major change was atmospheric. Carbon dioxide levels rose dramatically, creating what scientists describe as an enhanced greenhouse effect. Global temperatures began climbing, not by the few degrees we discuss in modern climate science, but by as much as 10 degrees Celsius in some regions. This warming wasn't uniform across the planet, it was most pronounced at the poles and least noticeable at the equator, which disrupted the temperature gradients that drive weather patterns and ocean currents. The polar regions, which had been cool but ice-free, became genuinely hot, while tropical regions became almost uninhabitably warm for many species. As temperatures rose, the chemistry of Earth's oceans began to change in multiple ways simultaneously. Warmer water holds less dissolved oxygen than cooler water, so as ocean temperatures increased, oxygen levels dropped. This process, called ocean anoxia, affected marine life in profound ways. Species that had evolved to thrive in oxygen-rich environments suddenly found themselves in conditions that challenged their basic biological processes. The warming also affected ocean circulation patterns. The deep ocean currents that had been carrying oxygen-rich water from polar regions to the tropics began to slow down and eventually stopped in many areas. This created vast regions of stagnant, oxygen-depleted water that became toxic to most marine life. What scientists discovered next was even more significant. The warming oceans began destabilizing methane hydrates, frozen methane deposits that had been stable on the ocean floor for millions of years. These deposits, formed by bacterial activity in ocean sediments, contained enormous amounts of methane locked in ice-like structures under the pressure and cold of the deep ocean. As ocean temperatures rose and currents changed, these methane hydrates began to melt and release their contents into the atmosphere. Methane is an even more potent greenhouse gas than carbon dioxide, so this release accelerated the warming process in what researchers call a positive feedback loop. The warming caused more methane release, which caused more warming, which caused still more methane release. Here's why this moment mattered so much. It demonstrates how Earth's systems are interconnected in ways that can amplify small changes into planet-wide transformations. The volcanic activity in Siberia triggered atmospheric changes, which caused oceanic changes, which released additional greenhouse gases, which accelerated the atmospheric changes. Each system affected the others in a cascade of consequences that gained momentum over time. This positive feedback mechanism is what made the Permian-Triassic transition so much more severe than other extinction events. While the initial volcanic trigger was certainly significant, it was the cascading effects through Earth's interconnected systems that created the truly planetary-scale transformation. The biological response to these environmental changes reveals something profound about how life adapts to rapid environmental shifts. Species don't simply disappear overnight. Instead, they face increasing stress as their environments change faster than they can adapt. The extinction process played out over several 100,000 years, but this is rapid in geological terms. In the oceans, the combination of rising temperatures, decreasing oxygen levels, changing chemistry, and increasing acidity created conditions that challenged fundamental biological processes. Marine ecosystems that had been stable for millions of years found themselves in entirely new environmental conditions within a geologically brief period. The great reef systems, which had taken millions of years to develop, were among the first casualties. The organisms that built these reefs required specific water chemistry conditions to create their calcium carbonate structures. As ocean acidity increased and temperatures rose, these organisms found it increasingly difficult to maintain their shells and skeletons. Filter-feeding organisms like brachiopods faced multiple challenges simultaneously. The changing ocean chemistry affected their feeding mechanisms, while rising temperatures increased their metabolic rates beyond sustainable levels. Many species had evolved to filter specific types of nutrients from the water, but the changing ocean composition meant that their food sources were also changing. Scientists have discovered evidence of this transition in rock layers from around the world. These geological records show a gradual decline in species diversity followed by a more rapid transition period where many life forms disappear from the fossil record entirely. What makes this pattern particularly significant is its global nature. The same changes appear in rocks from every continent, indicating that these were planet-wide phenomena rather than regional events. The selectivity of the extinction provides crucial insights into which biological strategies prove most effective during periods of rapid environmental change. Organisms with broad environmental tolerances, flexible diets, and rapid reproductive cycles were more likely to survive. Those with highly specialized requirements, slow generation times, or dependence on complex ecosystem relationships were more vulnerable. The terrestrial response was equally dramatic but followed different patterns. Land-based ecosystems faced rising temperatures and changing precipitation patterns as global weather systems shifted. The massive forests that had dominated Pangaea's landscape experienced widespread stress as rainfall patterns changed and temperatures rose beyond optimal ranges for many plant species. The seed ferns that had been so successful during stable Permian conditions proved particularly vulnerable to rapid change. These plants had evolved highly efficient but specialized reproductive systems that worked well under predictable environmental conditions. When those conditions changed rapidly, many species couldn't adapt quickly enough to survive. What scientists find most remarkable about this period is not the extinction itself, but the selective nature of the biological response and the speed of subsequent recovery in some lineages. Some groups of organisms proved remarkably resilient, while others that had been successful for millions of years disappeared entirely. This selectivity provides crucial insights into which biological strategies prove most effective during periods of rapid environmental change. The groups that survived often had certain characteristics in common. They were generalists rather than specialists, they had broad environmental tolerances, they could exploit multiple food sources, and they had relatively rapid reproductive cycles that allowed for quick adaptation to new conditions. The aftermath of the Permian-Triassic transition created a fundamentally different world. Earth's biological systems had been reset in ways that would influence evolution for the next 250 million years, including the path that eventually led to human civilization. The early Triassic period that followed shows us something remarkable about life's resilience and capacity for innovation. Rather than taking millions of years to recover, biological systems began adapting and diversifying relatively quickly in geological terms. Within a few million years, new species had evolved to fill ecological niches left vacant by the extinction. These new organisms often developed entirely different strategies for survival than their predecessors, leading to innovations that would prove crucial for future evolutionary success. Perhaps most significantly, the environmental pressures of the transition period seem to have accelerated certain evolutionary developments. The groups that survived and thrived in the post-extinction world included the ancestors of dinosaurs, mammals, and many of the major groups of organisms we see today. In a very real sense, the biological transformation of the Permian-Triassic boundary created the conditions that made our modern world possible. The Archosaurs, ancestors of dinosaurs and crocodiles, emerged during this recovery period with new physiological adaptations that gave them advantages in the changed world. Their more efficient respiratory systems and improved temperature regulation allowed them to thrive in conditions that challenged many other reptile groups. Ocean ecosystems recovered through the evolution of new types of marine life that were better adapted to the changed oceanic conditions. Modern coral reefs, dominated by scleractinian corals, evolved during this recovery period and proved more resilient to environmental fluctuations than their Permian predecessors. These new corals had different shell chemistry and more flexible symbiotic relationships that helped them survive in more variable conditions. The forest ecosystems that emerged were dominated by different plant groups, including the ancestors of many modern tree species. Early conifers expanded dramatically during the recovery, developing the drought-resistant and temperature-tolerant characteristics that would make them successful for the next 250 million years. These new plant communities created different soil conditions and atmospheric interactions that influenced climate patterns for millions of years to come. What makes the recovery period particularly fascinating to scientists is how it demonstrates life's capacity for innovation under pressure. Many of the biological strategies that emerged during the early Triassic, from new methods of photosynthesis to more efficient respiratory systems, represent evolutionary advances that proved beneficial long after the environmental crisis had passed. The lessons from 252 million years ago have profound relevance for understanding our modern world and the environmental challenges we face today. While the specific mechanisms are different, the Permian-Triassic transition demonstrates how interconnected Earth's systems are and how changes in one area can cascade through the entire planet. Climate scientists study this period because it provides a natural laboratory for understanding how greenhouse gas increases affect global systems. The rate of change during the Permian-Triassic transition was much slower than current human-caused changes, yet it still triggered massive system-wide responses. This comparison helps researchers understand the sensitivity of Earth's climate systems to atmospheric composition changes and the potential for positive feedback mechanisms. Marine biologists find the ocean chemistry changes particularly relevant to current concerns about ocean acidification and warming. The mechanisms that affected marine life 252 million years ago operate according to the same chemical and physical principles that govern today's oceans. Understanding how ancient marine ecosystems responded to changing conditions provides insights into how modern marine life might adapt to current environmental changes. The study of this ancient period also provides perspective on the relationship between environmental change and biological innovation. While the transition period was undoubtedly challenging for existing life forms, it also created opportunities for innovation and adaptation that ultimately led to greater biological diversity. This pattern suggests that life's response to environmental challenges often includes not just adaptation but genuine innovation. Perhaps most importantly, the Permian-Triassic transition shows us that Earth's systems have tremendous capacity for both change and recovery. While the transition period was challenging, it also demonstrated life's remarkable resilience and ability to create new solutions to environmental challenges. The story of 252 million years ago isn't fundamentally about an ending, it's about transformation and renewal. It shows us that Earth's systems are dynamic, interconnected, and capable of remarkable shifts. It demonstrates that life is both more fragile and more resilient than we might expect, often in ways that surprise us. Most importantly, it reminds us that understanding these natural processes helps us better understand our own place in Earth's ongoing story. The same systems that govern climate, oceans, and life 252 million years ago continue to operate today. By studying how these systems responded to major changes in the past, we gain valuable insights into how they might respond to changes in the future. The Permian-Triassic transition represents a turning point that shaped the biological trajectory of our entire planet. It's a reminder that Earth's history is not a series of separate events, but a continuous story of interconnected systems adapting, changing, and creating the world we inhabit today. Understanding this story helps us appreciate both the complexity and the resilience of the planetary systems that sustain life, including our own. In studying Earth's deadliest day, we ultimately learn about life's greatest strength, its capacity to adapt, evolve, and create new possibilities even in the face of the most challenging circumstances our planet can produce. This ancient event reminds us that while environmental changes can be dramatic and challenging, they also create opportunities for innovation, adaptation, and the emergence of new forms of life that might never have evolved under stable conditions.